Okay, so hopefully you now know in cupcake form how to tell the difference between mesons and baryons. Remember, mesons are made up of two things, a quark and an antiquark, and baryons are the heavier ones, and they're made up of three quarks. So that's not all of the standard model. We still have another row, a column to add, and this is due to forces. Okay, so we have some particles that are actually responsible for forces. So forces. Why does the nucleus not fly apart? If all the protons within it are positively charged, then electrostatic repulsion really should make them fly apart. The reason that is because there's another force holding them together, which is actually stronger than the repulsion from the protons from the protons. So there must be another force holding them together that over the short range within a nucleus is stronger than that repulsion. This force is called the strong nuclear force, and it is the strongest of the four fundamental forces, but it's also extremely short range in action, so it only works over a really, really short distance. The strong force is only experienced by quarks, and therefore by the baryons and mesons that are made up from them. The weak nuclear force is involved in radioactive beta decay. It's called the weak nuclear force to distinguish it from the strong nuclear force, but it's not actually the weakest of all the four fundamental forces. Again, it only acts really, really small distances. And the final two fundamental forces are gravitational and electromagnetic forces. The latter, the electromagnetic forces, being described by Maxwell's equations. They are very, very complicated. They're university physics. But if you're interested in them, feel free to have a read about them. And both of these forces have infinite range. Okay, they do get weaker as you go away, as you go further from them, but they still have infinite range. So there's a table, which is really the table that you need to know about. So strong nuclear has a small range, it's very strong, and it holds nucleus in the atoms. Weak nuclear has a really small range, is relatively strong, and it holds electrons in the atoms. Electromagnetic has an infinite range, is quite strong, and example effects of beta decay and decay of unstable hadrons. And gravitational is infinite, but is relatively weak compared to the rest of them, and it holds all matter in planets, stars, and galaxies. It may be surprising that gravity is the weakest. It's still very, very strong, but the others are even stronger. However, if the electromagnetic and strong nuclear forces were not so strong, then all matter would be easily broken apart and just nothing would exist. So again, I'm going to put the videos in for you to watch. So what causes the forces? Now these are a new particle called bosons. Okay, and bosons are something called exchange particles, and the way that they are exchanged depends on the force. Okay, so this diagram here is kind of a very fundamental explanation of it. You don't really need to know how they work. It is quite a complicated way that they work, but it's the way that they're given exchanged to other things. So you can see here, if you've got two people on skateboards here, and one gives a ball to someone else, they push away from each other. Okay, but if they were facing away from each other, they both threw the ball away from each other in the opposite directions, then they would be attracted towards each other. And that's a very, very simple way to explain how bosons work. All you need to know is what are bosons. You don't need to know how they work because it's really, really complicated physics. So what are bosons? There are four bosons. The last one isn't really included in the standard model because it doesn't quite fit in. So there are four bosons. The one responsible for the strong nuclear force is called the gluon. It glues them all together. The weak nuclear force is caused by the W and the Z bosons. They both do very similar things. Electromagnetic force is caused by the photon, and gravitational forces are caused by gravitons. The reason that the graviton has an asterisk next to it is because it doesn't quite fit in with the standard model. So these four, so gluon, W and Z, and photon, those four are in the standard model. Graviton's not included because it doesn't quite fit in. Okay, so much work has been done over the last century to find theories that combine these forces. There's been much success with quantum electrodynamics in giving a combined theory of electromagnetic and weak forces. And much work has been done to combine this with a strong force to provide what's known as a grand unified theory. And the video that I'm going to show to you will explain that a little bit more. But unfortunately, gravity is proving much more difficult to incorporate consistently into the current theories to produce what would be known as a theory of everything. Therefore, gravity is not included in the standard model. So far, this has not caused significant problems because the relative weakness of gravity and the tiny mass of subatomic particles means that it doesn't appear to be a significant force within particle physics within the nucleus. But yeah, it's a bit frustrating for scientists. And finally, the Higgs boson, just for interest really, because it's quite a recent discovery. The Higgs boson is basically something that we think is responsible for mass of things. So a theory postulated the existence of a further boson called the Higgs boson, which isn't involved in forces, but it's what gives particles mass. Attempts were made to verify its existence experimentally using the Large Hadron Collider, and in 2012 they discovered it. And I can tell you I had a party when they discovered it, because that's how much of a nerd I am. This particle is consistent with the Higgs boson predicted by a standard model. So I'll get you to watch a video on that as well. But just to summarise, we've got our full standard model now. So we've got our quarks, we've got our leptons, and we've got our bosons here. Okay, and that is your full standard model. Remember, quarks and leptons make up matter. Quarks make up protons and neutrons, and you can get two different makeups of quarks. You can get quark and an antiquark, which is a meson, and you can get three quarks, which make up a baryon. Okay. Just one last page to go through in this video. Beta decay and the antineutrino revisited. So we know that we've talked about how antineutrinos and neutrinos are both emitted in beta decay, depending on which beta decay it is. So beta negative decay, we know that a neutron changes into a proton and an electron and an anti-neutrino are given out. But how does it give out an electron if there are no electrons in the nucleus? Well, that is because of the quarks and what happens with the quarks. So a neutron changes into a proton and an electron and gives out an antineutrino. So what happens inside the neutron is a neutron is originally down, down, up, but it then, one of those downs flips and changes into an up quark. So a down quark changes into an up quark. Okay, so at a fundamental level, a down quark decays into an up quark through the emission of a W boson. Only the weak force can cause such a change in flavour, so from one quark to another, and the electron is forced out at high speed due to the nuclear forces. Okay, and that's basically how it happens on a very fundamental level.